and go full screen. Okay. So last time we started talking about AC power and introducing some concepts around AC power, which we're going to talk about quite a bit as we move forward. We talked also about transformers. We want to say a little bit more about transformers as well. Transformers, you're going to see those in a lot of the problems that you have around AC power. Okay. So last time what I did was I introduced the concept at the beginning called RMS, root mean squared. Okay. Now, the reason we do this is because when we talk about DC waveform, it's pretty obvious. There's only one number you can associate with it. Up until now, we've taken this waveform here and we've gotten rid of the fact that this guy depends on time, right? We've used phasors, right? So with phasor, we've used the amplitude and the phase shift. We're going to keep using phasors, except instead of using the amplitude, we're going to use the RMS value. So last time we talked about what's the relationship between the RMS value and the amplitude.
The RMS value is 0.70 times the amplitude.
Yeah, the RMS value is the amplitude divided by square root of 2. Okay. Now I have a set of slides that I uploaded over the weekend. I'm going to basically use the same set of slides. I'm going to show you here today. You can run into a lot of formulas with power, and it's unfortunate. What I have in that slide deck, and we'll get to it today, is a summary of all the formulas. All right, that I think distills it down pretty clearly what things you need. And then we're going to walk through problems to look at how we apply those different things. Okay. So we're going to use RMS. So from this point forward, everything will be clearly, everything is going to be in terms of RMS. All right, because it's easiest to do that with power. That is actually the most common thing to do. If you go into the lab and you use the multimeter, or if you pick up a multimeter, usually if you put that meter so that it measures AC voltage or AC current, it's measuring RMS. All right, that's the number that it tells you when you're measuring an AC waveform. Okay, so it's very common that we use that. Engineers always use the RMS number. Now, what we talked about last time is, okay, if I'm putting power into a load, right? So you guys know this already, right? Power is what? And somebody online, what is the definition of power?
Voltage times current.
That's the result, but the true definition.
Energy per second, the energy, right?
It's the rate at which energy is consumed. That is the true definition of it. That just so happens to also become voltage times current. Okay, so it is V times I, right? There is no doubt about that. But the definition of it is that it's the rate at which energy is consumed or generated in a device. Okay, and so what we looked at is that's pretty straightforward. If you're talking about a DC voltage source, right, in a resistor, then there is only one value of the voltage and there is only one value of the current at all times, and everything's very straightforward. All right. In the case of an AC situation, that's a little bit different. So what I have here, so what we looked at last time, I basically said, what happens if I have a 100-watt light bulb and I hook it up to a voltage source? All right. And this voltage source is going to be 120 volts RMS, root mean squared. Okay. So this means that what's the peak value of this guy? What's the, yeah, 120 times square root of 2, which works out to about 169, would be the peak value.
Isn't that just A?
Yeah, that's A, the amplitude, right? So we're going to use the 120 RMS, right? So in this case, I have a 100-watt light bulb. And what I say is if I looked at the voltage would look like this, what I have shown here. If I have just a resistor, what would the current look like? If I had to draw the current, what would it look like?
Would it be shifted? No, it'd be double, right?
So what is the light bulb? What type of load is it? What type of impedance is the light bulb?
Resistant only and no shifted.
Yeah, so if it's a resistor, right? If I just have a resistor, how much phase shift is there between voltage and current? None, right? So if I have a cosine voltage like this, I'd have a cosine current. So it would look like this. I've blown it up because for a 100-watt light bulb, it wouldn't be this big, all right? But it would look something like that. Let me be clear about it. Like that, okay? So if I talk about the power, what we do is we say P of T equals V of T times I of T. And what we get is this. This is the power, we call this the instantaneous power. This is what we talked about last time, instantaneous power, meaning the power at any given time. Now, is that 100 watts? I said this is a 100-watt light bulb, but is that 100 watts? Well, it looks like it goes from 200 to 0, right? The average of it's 100 watts, and it's always positive. The fact that it's always positive, the fact that this voltage goes positive and negative, but this power, the minimum value here is 0. This guy's always positive. What does that mean? The fact that P of T, the fact that the power is always positive, what does that mean?
It's only consuming, it's not
Always
generating.
consuming.
It's always consuming. Yeah, it's always consuming. It's never generating. If I have negative, that means I'm sourcing power out. Okay. If it's positive, I'm just always absorbing it. Okay. So in this case, what this means is this light bulb is always absorbing power and taking that power electrically and converting it into heat and to light. Okay. That's basically what it says it's doing. Now, what we talked about though is the situation can change a little bit. This guy right here, that picture I have at the top, how does the frequency of that relate to the frequency of the voltage?
Twice.
It's twice. All right, that's twice the frequency. And the formula specifically, if I talk about the peak values here, is written out like this, right? So I have, in this case, the current and the voltage are in phase with each other, so I get this cosine squared, so it becomes this whole thing. Now we're not gonna do trig identities with this. We're gonna jump away from those today, all right? But we see some important results with this. So what we said is we take the average values. The average value is just what you learned in calculus about computing an average. You sum up and then you divide by the amount of time. So you take the average over a period. So as I look at one period of the voltage, which I've marked out with these red lines, you see the average of that is 100 watts, okay? So what happens, first of all, let me stop there. Any questions about that? Right? It's pretty straightforward to understand that. What happens when I have a situation where I have a general impedance, right? And so in particular, I started out and said, what happens if this load is an inductor? Okay, if this load is an inductor. So if I talked about the impedance of an inductor, Z equals J omega L. What does that mean in terms of the magnitude and the angle of that impedance? Somebody online, what's the magnitude and angle of that?
2 pi L, and then it's got a shift of 90.
Yeah, so omega L or 2 pi FL, right, with an angle of 90 degrees, okay? So what that means is what? So if I'm talking about this guy, if I'm thinking in terms of Ohm's law, right, V equals I times Z. So the way that I think about this is V equals I times Z. Those are all complex numbers. So when I multiply complex numbers like that, what's the relationship between the voltage and the current angles there? Atom. So the angle of the voltage equals what?
The angle I plus angle Z.
Angle I plus angle Z. So angle Z is equal to angle of V minus the angle of I, okay? So essentially what that means in this case is that there's going to be a 90-degree shift between the current and the voltage. I don't care right now which direction. Is it 90 ahead? Is it 90 behind? Let's not worry about that. There's a 90-degree shift between the two, okay? We can talk more about which way it goes later. There's a 90-degree shift. If I had a capacitor, what would the difference be? Be a negative 90, right? So there's a 1 over J. Essentially, there's still a 90-degree shift. We're just talking about which direction. Do we go forward or do we go backward, right? So let's not worry about that. Let's just say there's a 90-degree shift for now, right? If I get in the situation where I have a 90-degree shift and I say, all right, well, let's do that P of t equals V of t I of t. Okay. If I do that, and here's my power now on the bottom, what do you notice about the power in this case? In the bottom.
It shifted
Yeah.
and it shrunk a little.
Well, yeah. So one thing that's true is if this guy up here is a cosine, right? This guy is cosine omega t. Down here, this guy has, what's the frequency of the power down at the bottom? What's the frequency of, if this guy's got a frequency of omega,
It would be 2 omega.
this guy down here is 2 omega. Yeah, but also he looks like he's probably sine, right? Because of just the way he starts at 0 right here. Okay, that's important. There is a shift, but that's not maybe the main thing. There's a shift also vertically, right? So what's the average value as I go through one period of that waveform on the bottom?
0.
0. So it's 0. So this is the weird thought. Now I have an inductor, I have an impedance here. So when this guy is positive, what's happening? What's happening here during the positive part? What's happening?
Absorbing?
Is absorbing. So here is absorbing power, right? And then down here is the opposite, right? He is he's supplying it or sourcing it.
This is in with the inductor.
Yeah, and it wouldn't matter. Why is this happening? It doesn't matter if it's an inductor or a capacitor. Why is that happening? What's true about the angle between the current and the voltage in that case? Well, they're 90 degrees apart. When they're 90 degrees apart, what ends up happening is that half the time energy is being absorbed, half the time energy is being sourced, right? Because this guy is an energy storage element, okay? And what we found, we went through this last time. I ended up with a definition, a couple sets of definitions at the end of the last class. All right. Basically, if I take that P of t expression and I write out that P of t expression and expand it with trig identities and everything, I basically end up with what I have right here, where I have this term I called real power. So this guy is real, active, or average power. I'll use all of those. And I will be honest with you, most of the time people say power. Instead of, they don't always say real power, active power, average power, they'll just say power. Okay. It is defined with a capital P. We very infrequently talk about P of t. All right. In problem 2, maybe problem 3 of this homework, I think I talk about that. But we stopped talking about P of t pretty quickly. We talked about capital P. Now, this guy right here, this is the average power, right? So what do we say was the average power in this case? If I'm looking at this picture.
The bottom one or top?
Well, so the top is the voltage here. So if I'm looking at this picture on the bottom,
Power, it's 0.
yeah, the P, the capital P, the average power is 0. Okay. So this is an inductor. The average power into an inductor is 0, but there is still current that's flowing through the circuit, right? If I have this circuit right here and there is an inductor, there is no power being absorbed on average by that load, but there is still current that's flowing. And we got to give some name to that, right? So what was the term we called that last time? We gave that a name. Reactive power. Okay. Reactive power. So there is real power, which relates to the power that is really going into doing active work. So when I say active work, I mean, if I have a motor and that motor is working at 1 horsepower, then there is 750 watts of real power on average that's going into that motor. If there's a 100-watt light bulb, there's 100 watts of average power going into that thing because there's work happening there. But if I have an inductor, I'm basically supplying energy and then it's giving it back. supplying energy and giving it back. Because that leads to a current that flows through the grid, we give it a name and we call it reactive power, all right? Or Q is the term for it. Real power and reactive power, we call it, so P and Q, all right? And what we did was we said, okay, if you expand that P of T term, what you see here is I basically have sort of a general formula for P and Q, and I can see that those values, which we just define, all right, are basically the coefficients on those sine and cosine terms. And if I take the average value of P of T, what's the average value of a cosine or a sine? Always zero, right? So the average value of this guy is going to be P, all right, if we look at that. All right, we're not going to deal with the time domain expression much. I think there's one problem in the homework where basically you got to solve for the currents in the circuit, and then you look at these formulas to say, well, I think I ask you, what's the coefficient on the cosine 2 omega t term? What's the coefficient on the sine 2 omega t term? Okay. So we get these relationships for real power and average power, and there's work that we got to do to figure out how to use all this stuff. So we're going to use this idea of phasor diagrams a lot. So what I have here is, sort of a couple of different cases. So I have a load that has this voltage applied to it. Okay, so the circuit would be
Just a resistor, right?
yeah, just a resistor. I'm going to call it a Z, right? But if I have a resistor, then my Z is this 144 ohms with an angle of 0. Okay. So what I did here is I said, okay, well, if I look at the peak value, so this is as we've always done it, peak value 120 times square root of 2. All right. The current peak that I get is 1.1785 amps. So if I go through and I do the calculations here of P and Q, right? The P that I end up with is 100 watts. The Q in this case, the Q is the reactive power. The important thing maybe here is to look at this. Phi V minus phi I. There is this dependence on that guy. Phi V minus phi I, we said this already, V equals I times Z, right? So if I look at those angles there, that tells me the angle of the voltage equals what again?
Angle of the current plus the angle of the impedance.
Angle of the current plus the angle of the impedance. So if I'm talking about a resistor, what's the angle of the impedance? 0.
0.
So how much phase shift is there between current and voltage if I have a resistor? 0, right? So if I have the sine of 0, what's that become? 0, right? There is no Q in that case. And I end up with a purely imaginary thing. What's going to happen if I had an inductor, just an inductor? There'd be a 90-degree shift between the current and the voltage, right? And so would I have any of this? So here's my P. This is P. This is Q. Would I have any P in that case if there's a 90-degree shift? No.
No.
Right? So in the case of a pure inductor, if I plug in all the terms there, I end up with just 100 sine 2 omega t, right? And what I see at all times is my power has 0 average. Now, in reality, you would never just power an inductor. In fact, Duke wouldn't even let you do that probably, all right, where you would just power an inductor. You would have a separate situation. Most likely what you have is something in between, right? You have an R in series with an inductor of some kind. So if I had that, what would you expect the phase shift to be in that case? So if I had R plus j omega L, that's my load. What would you expect the phase shift to be in that scenario?
Negative 90.
So if I have R plus j omega L, where would that be? Where would the angle of that be?
With the j omega L. With the j.
So if it's R plus j omega L, so j omega L definitely has 90 degrees, right? R has 0, but that's a vector, isn't it? R plus j omega L, where would that be?
Wouldn't that be at 45 degrees?
Well, it's not, it all depends on the values of R, omega, and L, but it would be certainly in the first quadrant. So 45 degrees is an option, but it could be 30 degrees. It could be 10 degrees. Well, yeah, sure. So specifically, it would be tan inverse of omega L over R.
But
Right.
specific first quadrant, and that's
It's going to be in the first quadrant, right? And I know it's going to be in the first quadrant because R is always going to be positive, isn't it? Never going to have a negative resistor. Also never going to have a negative inductor or a negative frequency, right? So I'm always going to be in the first quadrant when I have this situation. So in that case, if I'm in the first quadrant, so we talked about so if I had a pure resistor, my angle is 0 degrees. If I had a pure inductor, my angle would be 90 degrees. If I have a combination of the two, I would be, 30 degrees, 45 degrees, somewhere in the first quadrant. What do you think is going to happen in that scenario? If I have that, there's going to be some phase shift between the current and the voltage, right? But it's not going to be 90 and it's not going to be 0. So in that scenario, what are you going to have? You're going to have some P and some Q, right? So if I have a situation like this guy right here, let's say I had R plus j omega L like this, right? And I chose the same magnitude of my impedance, 140 ohms, with an angle of 45 degrees. Well, that puts this guy up here, okay? Now, we can ask ourselves, what would the angle of the current be in that case? What would the angle of the current be? If I wanted to figure out what the angle of the current is, well, I've got it here as negative 45, right? So, okay, well, there's the answer. But how can I know that that's negative 45?
It's the angle of B minus the angle of V.
Yep, if V equals I times Z, then phi V equals phi I plus phi Z, okay? So if I do the math right there, right, it's going to tell me that if phi V is 0, that's equal to phi I plus, in this case, 45 degrees. So that tells me the angle of the current is negative 45 degrees, okay? So we'll have more to say about this, how we determine that this guy's leading and lagging. But what I see from this right here is that overall, looking at this, I get some P and some Q. So I think my slides got mixed up. Where is it? Yeah, this is the picture. If I'm looking at that, all right, this is what the power looks like. So this guy spends some time below 0. So there's the 0 line right there. All right. Still 200 watts peak to peak, right? But this guy is positive most of the time and negative sometimes, right? The average in this case would be 70.7, right? Because that is the P value, right? And then there is this sort of 100 watts peak variation happening on top of that, all right? There's a lot we can say about that. We don't need to say a whole lot about that. There's a whole approach to sort of solving these problems, okay? But the basic idea is that once we know what the impedance is, we can determine whether or not that impedance is all Q, all P, or some P and some Q. And for the most part, the loads have some P and some Q, okay? All right, questions about that? All right, so what I want to jump ahead on here, all right, so we talked a little bit last time, just to remind ourselves, right? DC circuits, you had the power equals voltage times current, right? Very straightforward, right? And then since you were only talking about resistors, you could then say, well, if I know I have V and I, you could rearrange that, guys. So you could say P equals VI. You could also say what through Ohm's law? You had two other terms you could use.
V squared over R,
V squared over R
I squared R.
and I squared R. Okay, so there's those two other terms that you could use. Now, if we look at the formulas that I gave you there, so this is our P of T, right? And if I go back and I look at the the P and the Q. So this guy here is the P. Okay. This guy here is the Q, like that. If I look at that, if I know that the RMS value is the peak divided by the square root of 2, one of the things that we see from that is, well, if I did IRMS times VRMS, that's the same as I peak divided by root 2 times V peak divided by root 2, which is what? What's square root of 2 times square root of 2?
2.
2, right? So basically, what we say is the formulas lose that over 2 situation, right? That over 2 guy goes away if I use RMS, VRMS, and IRMS. Now I get this other weird term here with this cosine, right? But what would be true if I had a resistor? What's the phase difference between current and voltage when we have a resistor?
0.
Still be 0.
0, right? So the example I think of is, okay, so if I had a 100-watt light bulb, okay, that means it's 144 ohms typically. If I hooked up that 144 ohm resistor to 120 volts DC, the current would be 0.833 amps, the power would be 100 watts. And that power would always be 100 watts. There'd be no variation to it as a function of time. It would just be 100 watts. If I hooked that same light bulb up to this voltage source, right? What's this? This guy's 120 square root of 2 is his peak value. What's the RMS value of this thing?
120 square root 2.
Well, the RMS value would be 120.
30.
Yeah.
Oh, because it's under square root 2, yeah.
Yeah, the peak value is 120 root 2, or about 169. And so what I see from this is if I look at the DC version of this circuit, 120 volts, 144 ohms, the DC circuit situation, I get 120 volts, 0.833 amps continuous, 100 watts continuous. If you look at the AC circuits, 120 volts RMS, 0.833 amps RMS, 100 watts average power. And so we use the RMS number because basically if we were only talking about resistors, everything is the same, right? Now, once you start talking about a situation where I have some phase shift between the current and the voltage, then this cosine guy comes into play, which we'll give a special name to. All right, but effectively engineers like it because it simplifies the math, gets that over 2 out of the way. All right, and it makes everything seem like it's just like DC circuits again. All right, so that's why we do it, and we will, unless stated otherwise, things would be in terms of RMS. Right, most of your problems are going to be in RMS. Okay, so all right, there is effectively a simpler way of doing this, right? That doesn't involve the time. Okay, so specifically, all right, where we left off with was we had this P of T equals this guy. All right, and I gave the definition that P is VRMS IRMS times cosine phi V minus phi I. Okay. And Q equals VRMS IRMS sine phi V minus phi I. Okay. Now, if I have that relationship right there, this is my P and this is my Q. Okay. How can I, is there anything, look at, so phi V minus phi I. So we said that that's the impedance angle. All right, so I'm just going to do it that way. I'm going to say it's the impedance angle phi sub Z. Okay. There's a reason why I have summary of all the formulas because there's many. If I had that, if I had a P, this quantity equals something times the cosine of an angle. And this guy is something times the sine of an angle. Like, let's just say for sake of argument, VRMS, IRMS, let's give it a number, right? VRMS and IRMS, let's say that was equal to 10. All right, VRMS times IRMS, let's say it was 10. So that means I got P equals 10 cosine phi z, and q equals 10 sine phi z. Doesn't that somehow look like what we would see with vectors?
Yeah.
Right? So I basically, if I have a vector, it's got a, how do you write a vector in, you say it's cosine times the magnitude and sine times the magnitude for the different parts, right? So which part has the cosine and which part has the sine? If I'm talking about a vector, a complex vector.
Cosine has the real, sine has the imaginary.
Cosine is the real part and the sine is the imaginary part. So effectively, what we noticed, and there's no definition, there's no derivation of this, it's just a definition. People noticed that if you look at this P and you look at this Q, it looks like they are components of a vector. And so people said, well, we're going to define a new term. We're going to call it complex power. And we're going to say that this complex power, we're going to call it S. All right. And that S is equal to VRMS, IRMS, cosine phi z, plus VRMS, IRMS, the J, sine phi z. You guys follow? Basically, somebody just noticed that these two terms look like the real part and the imaginary part of a vector. And so they said, well, cool. Then let's go ahead and say that that is just simply a vector. Okay? Because it is. Those form two components of a vector. And we call that S. All right? And I'm going to call that S complex power. Like that. All right, we call that as complex power. So what would that look like? Well, if I go through here, so here's how I write this out here. So this complex power is this VRMS, IRMS cosine phi z plus J, blah, blah, blah. All right. If I look at this, this is P plus JQ, right? And so we draw it out like this. Now, this vector S, without going too far in this, where is it always going to be? What two quadrants is it going to be in?
1 and 2.
Not 1 and 2.
1 and 4.
1 and 4.
1 and 4. Right? It's going to be over here. Here's 1, and here's 4. It's going to be in quadrant 1 so the angle of this is phi sub z, the angle of the impedance.
Phi sub z is then phi v minus phi of I, right?
Yeah. So it's the shift between the voltage and the current,
Okay.
right? Phi sub z is the angle of the impedance. So what puts the angle of the impedance in the first quadrant? What makes it positive? In an R plus an L, an inductor and a resistance. What's going to put it in the fourth quadrant?
Capacitor.
Capacitor. Yeah, if I had a capacitor and some resistance, it's going to put me in the fourth quadrant. The way we look at this, sometimes people call this complex power relationship here. It says that the S, right, the hypotenuse of this. So if I look at this as a vector, I can also think of it as a triangle, right? So sometimes people refer to these things as the power triangle, right? Because I'm always going to have this guy looking like a triangle of some sort. And the angle of this vector is phi sub z, right? And then I've got the imaginary part of it is the Q, the real part of it is the P, all right? And so I have these definitions for those two things there. All right, so that's important, all right? We can use that and we will use that quite a bit as we move forward, all right? This is nice because now, like I said right here, I can forget the time varying parts and talk only in terms of P and Q. Because that's when we have time variation, the math is nasty. It's not very useful. We talk only about the P and Q values.
So this is a vector. So complex power is essentially a vector.
It is. It's a vector that's just defined. We just made the definition because somebody looked at these terms right here, right? These two terms here on the slide and said, those look like the real part and the imaginary part of the vector. So let's just make the definition and call complex power a vector where the real part, the P is the real part and the Q is the imaginary part.
So what is the magnitude and direction of this vector mean?
Well, what is the angle? So the direction of it is what?
The direction is 5 z.
Which is what? The angle of the impedance, right? So it tells me that if I have a resistive load, how much, so if I have a resistive load, how much imaginary part am I going to have? 0, okay? If I had a purely reactive load, so a pure inductor or a pure capacitor, how much P am I going to have? 0, all right? And so the meaning of this guy right here effectively is the meaning of the direction of this is related to the angle of the impedance. So basically, if I have some imaginary part to this vector, then I have some phase shift between the current and the voltage, and I have some reactive power. All right, so in other words, I've got some impedance there that's causing a phase shift, and I have some energy storage going on. I'm not just purely converting energy, electrical energy into heat or whatever. All right, make sense? Okay. All right. Questions about that up till there? All right. Keep going. All right. So now what we do is we define that guy as the complex power. And if we look at this, the magnitude on this guy, VRMS, IRMS, if I just call that the magnitude of S, I give that a definition. All right. The magnitude of this guy is called apparent power. All right, so very quickly, we have now talked about P, Q, S complex power being P plus JQ, and the magnitude of S being apparent power. This is apparent power. This guy is complex power.
Those definitions are important when describing what exactly between complex power and apparent power, just not involving the angle.
So yeah, the magnitude of the complex power vector is the apparent power. That's all it is. All right. Now, one thing I have here. All right, so I'm going to jump ahead to some summaries here. All right, so I said I've got, so in my notes, right, I basically have the definitions of each of these guys. So the real or active power, the reactive power, the apparent power is the magnitude of that vector, okay? And I have the equations here in terms of RMS and peak, all right? Important thing here is we talk about a couple of different units to distinguish between them. All right. Real power gets watts. Okay, which is important. Watts is this guy is the one that equates to real honest to God work that's happening in the world. Reactive power gets units of VARs, all right, or volts, amps, reactive. If you look at these guys, right, it's still volts, amps, volts, amps, multiplied by this cosine and sine. What's the angle of a cosine or a sine? Sorry, not the, what's the units, sorry, of a cosine or sine?
Radians per second or degrees.
It's gain, it's the multiplier. Doesn't have.
It's just a multiplier. Yeah. So the angle that goes in there would be in radians or degrees, but cosine or sine themselves are unitless, right? So so all of these guys this guy is volts times amps. This guy is volts times amps. This guy is volt times amps. So we distinguish between them, we arbitrarily gave them new names for their units. All right. So if I'm talking apparent power, I say VA or volts amps. If I say real power, we're talking watts. If I say reactive power, I'm talking VARs, volts amps reactive. Okay. Now, most commonly you will hear watts and VARs. You don't talk about apparent power as much. All right. Now you may have seen, one common place where you see volt amps or VA. If you ever bought a UPS unit for a computer, backup unit for a computer, right? You'll see that it says 120 VA or something like that, right? Or 1,000 VA or 2,000 VA. So those guys sometimes have units of apparent power, okay? What you hear oftentimes, and if you guys have, worked at, some of you guys have done internships or whatever, you may hear VARs, right? Often. People, instead of saying Q, will just say how many VARs are there or how many watts are there. So those terms are important. Okay. So in dealing with these problems, so we got to get some definitions out, right? We're going to deal with a lot of examples to say, okay, well, if faced with a particular problem and we want to calculate, watts and VARs, how do we approach it? Okay. Got to get these definitions out there and understood. All right. So to differentiate there, the complex power is the name of the whole in general of that vector. Okay. The name of that vector specifically, all right, is complex power. Okay. And the magnitude of that guy is the apparent power. Okay. All right. Questions about that?
So I get that they're called watts and var, but is the relation specifically because of the angle, like cosine and sine? Like if I were to see an equation, I immediately know I'm working in watts. If I'm looking at or real or active power because of cosine.
So what you're typically going to see in the homework or in the real world is you'll say, I have a load that absorbs a certain amount of watts, and it has a term I haven't defined yet, but a certain power factor. All right, which allows me to determine which one I'm referring to. All right, so
Gotcha.
I need to get to that definition of the power factor,
Okay, nice.
which is coming up here in a second. But I want to let me jump to that, I guess. Power factor is defined as that cosine. All right, so very quickly I have gone from, well, power is volts times amps to, well, no, it's actually, I got watts and apparent power, complex power, reactive power. Now I got a power factor, right? We introduce a lot of terms really fast. So we're going to do a lot of examples, and I have in here, right? So I introduce a lot of summary information here. And in fact, by the time we're all done, thought I had another summary slide. This is actually maybe the key summary slide, I think, here, right? There's not that many formulas. We're going to talk about a summary slide. We're going to talk about a process for approaching the problems. Okay, so we're trying to manage this, because what I found when I first started teaching this stuff, people will get really blown away by it really fast because there's so many different things, but it's actually pretty straightforward. All right, and hopefully you'll see that over the next couple of lectures, right? That it is pretty straightforward. And don't get intimidated by all these terms. All right, the other definition here is this quantity called power factor. All right, the power factor is the cosine that exists. So that cosine phi v minus phi I, that guy is simply called the power factor. Okay, and so utilities use that term a lot. All right, we'll look at some examples, but utilities will say, I'm delivering load to a customer that has unity power factor, or typically a 90% power factor, 95% power factor. The idea would be, if I have a unity power factor, the cosine of phi z is equal to 1. So phi z is equal to 0. That means the current and the voltage are aligned with each other, right? Current and the voltage are aligned with each other. Unity power factor is sort of the ideal situation that utilities like to have. Why? Because if there's a shift, then they are providing current to your inductances that you could actually provide yourself. Okay. That means that you would reduce their costs if you could maintain closer to a unity power factor. So we'll talk about that later, okay? But this idea is important. So today we're just trying to cover some definitions. Power factor is just a straight up definition. What would my power factor be if I had an inductor or capacitor?
It'll be 0, right?
Be 0. Yeah, it'd be 0 because the phase shift between the voltage and the current is 0, or is 90 degrees. Sorry. Thank you. See, you guys are getting this. Voltage is 90 degrees. All right, between voltage and current. So the cosine of 90 degrees would be 0. All right, so there'd be effectively no P and all Q, because the sine in that case is 1. All right, so all sorts of terms to this. Now, one thing that I do want to cover here. All right, let me add slide at the end here. And let me copy this picture over for myself. Oh man. Okay. So this was my picture I had for that complex power vector, right? That complex power vector, if I wrote it out, was S, oh man. S equals VRMS IRMS cosine phi z plus J VRMS IRMS sine phi z, like that, okay? So we also said, since V equals I times Z, right? That's just our vector Ohm's law, right? The angle of the voltage equals the angle of the current plus the angle of the impedance. So the angle of the impedance is the angle of the voltage minus the angle of the current, okay? So the way we originally came into this, guys, we said this is VRMS, IRMS, cosine phi V minus phi I, plus J times VRMS, IRMS, times sine of phi V minus phi I, like that, okay? If I look at that for a second, right, does that look like it at all relates to what would happen if I multiplied voltage and current? So voltage, remember, voltage is a vector, right? Voltage is a vector. Let's say it has an RMS magnitude and an angle, this, and I has a magnitude like this, right? What happens if I take V times I, and in fact, let me specifically say V times I conjugate, right? What does it mean to take the conjugate of a vector?
It's 1 over the value.
Not 1 over the value. It's I flip the sign on the angle, right? So essentially what I would have is, if I did I conjugate would have the same magnitude, but his angle would be negative I.
Oh.
Right, it's a 180 degree turn on the angle. So if I had, if I was, 1 amp with an angle of 10 degrees, it would become 1 amp with negative 10 degrees. All right, it would basically be what I would get as a result of that. So what would that do? Let's say, so if I had this definition of V and I said, well, let's just compute V times I conjugate just for fun, right? What would that be?
Same magnitude.
Capacitor was involved?
Well, its magnitude would be VRMS,
Yeah,
IRMS.
the angle.
And then it would have, so let's do this. So what I want to do is I want to do this in terms of real and imaginary parts here for a second. So what would
Maybe
so its magnitude is VRMS, IRMS. What would its angle be?
You add the two.
Phi V
Plus phi I.
minus phi I
2.
minus phi I. Yeah, because so I'm adding the angles, right? So it's V times I conjugate. So I conjugate has an angle of negative I. So I'm adding the angles. So angle voltage plus the negative angle of the I. If I expanded this out into its real and imaginary parts, what would that equal?
One would be a cosine, the other one would be a sine.
Yeah, one term would be a cosine, one term would be a sine. That's the same as complex power, isn't it? Right? So that means that this S is also V times I conjugate. All right, so this is one of those things where we've just derived everything that we need to know. All right, now we just need to know how to use it in some problems. Okay. All right, so there's a lot of stuff going on with these guys, right? Lots of different problems and different little things that we can solve. Okay. But we have the key relationships there. And so this summary slide, there's two kind of key summary slides that I have. This is one of them here, right? So here, what I have is that picture. So I've defined for you the apparent power, the real power, the reactive power, the power factor, and then this relationship between, so the complex power is P plus JQ, and there's the formulas for it. Right, and that is also equal to V times I conjugate. All right, so with that set of relationships, we primarily have everything we need to know to be able to solve all these problems. All right, these are the things that we're going to need to be able to deal with to approach these problems. Okay, so let's look at sort of a typical sort of problem that we might face. So let's say I had this situation. So I got a voltage source, and that voltage source is hooked up to some impedance. Okay. And let's say this voltage source is 120 angle 0 degrees. Okay. And this is RMS. Like that. And let's say that this guy here is 1,000 watts with a power factor of, well, let me not do it that way. Let's say he's 1,000 watts. Let's say he's 1,000 watts and 100 VARs. All right, and we want to approach this guy and we want to figure out what's the angle of the impedance, and we want to figure out what's the current phasor. Okay, so how would we approach that sort of a problem? So it's 1,000 watts and 100 VARs. Okay, so we want to know the angle of the impedance, and we want to know what the vector for I is. So where do we start?
Let's start with the angle.
Start with the angle. So how can I get the angle?
Well, we already have angle of V, right? It's 0 degrees, so we just need to find the angle of the current.
So how would I get the, so what do I have here that'll tell me this guy's 1,000 watts and 100 VARs? P and a Q.
The real and the, yeah.
P plus JQ. All right, so Stephen, which one is which?
Bar is your reactive, and then 100 watts is your real.
So 1,000 watts is my real, and 100 VARs is my imaginary, right? My reactive. Okay. So that guy right there, so I can look at that thing and say, okay, well, if I were to sketch that guy, all right, here's the real, and here's the imaginary. This guy would be like this, right? So this is 1,000. This guy is 100, right? This is phi sub z, right? And I've got that on my picture back there, right? So if I wanted to figure out phi sub z in this case, what would I do to figure that out?
Tangent.
Yeah, I can just say the tangent of phi z. Now this is a situation that's nice. So Yeah, I often use the angle command or whatever in MATLAB to do this, but I'm not going to have one of those weird second or third quadrant things where I got to add 180 degrees or whatever it is. This guy is always going to be in the first or the fourth quadrant. So I can just say the tangent of this guy is equal to what?
100 over 1,000.
Yeah, 100 over 1,000.
And then do the tangent inverse.
Yep, and then do the tangent inverse. So phi z would be equal to inverse tangent of 0.1, which is what in this case? It would be tan of 0.1. This would be about 5.7 degrees. 5.71 degrees, I guess I'll call it. Okay. So, all right, I've got what that is. Now, how would I figure out the vector for the current? How can I relate this to the vector for the current? Well, let's go to the formula sheet that we had there. The magnitude of S, right? So if I go up to my summary slide right here, right? So the apparent power is the magnitude of S, VRMS times IRMS, right? And I know enough to calculate the magnitude of S, don't I?
Yeah.
Because I know, well, yeah, so I know P plus JQ. So I can just say the magnitude of S is equal to the magnitude of P plus JQ, okay? Which in this case would be what? 1,000 squared plus 100 squared. And I take the square root of that. So that's not a whole lot more than 1,000, right? That becomes basically 1,005. What units do I give it? Volt amps.
Volts.
Volt amps. VA. Okay. Volt amps. So then if I want to relate that to an I, what do? Well, I say, yep, this guy is just simply VRMS, IRMS. Okay. My VRMS is 120. So I take that 1,005 and divide by 120 to get my IRMS.
Isn't it, so IRMS is I conjugate to the same thing?
No, IRMS is, so going back to the way we defined it here. So this summary slide helps a lot, I think, right? I guess I don't have the definition on it here. Maybe I should. So basically what I'm saying is that V, the phasor for that is VRMS angle phi V. I is got a magnitude of IRMS with an angle of I. Okay, so the magnitude of it is the RMS value. So the RMS values are not vectors; they're the magnitudes of the vectors.
It's also that I also had like the magnitude of S equals like V phasor plus the conjugate of I. So I thought we were solving for the conjugate of I.
So when we're talking about the magnitude here, right? So the apparent power is VRMS, IRMS. That's the magnitude of that vector, right? So I still got to get the angle, right? So when I do this, I'm going to get IRMS as a number, but it's just a number, right? So in this case, I'm going to get 1,005 divided by 120. So this guy's going to work out to IRMS equals 8.375 amps. And this is RMS. I'm not always going to write it out there, but I'm going to say it's RMS for now, right? All of our magnitudes are going to be RMS from this point onward. So for the next couple of days, I'm going to keep repeating that point. There may very well be a specific problem where you'll be given peak values. For the most part, problems on the test that you get, you'll just do them, right? They'll be in terms of RMS, and you'll do them. If I don't tell you otherwise, it's RMS. I don't usually run into people having problems on the test, losing points because they get it wrong. Where they lose points is when I specifically give them things in peak values. Then they start using the RMS equations. That's when you'll lose points. There was a question somebody was going to ask. I heard a so, and then the so faded.
So I think we can do that by without calculate the s, right? Because we have the phi z already, so we need the 1000 times the cosine of phi z and divide.
Yeah, so there's going to be multiple ways to do these problems for sure, right? So yeah, I could have used the P equation possibly instead of the S, the apparent power equation to do this. I still have to figure out the angle of I. If I want to get the phasor, right, I figured out the magnitude of it. How do I get the angle?
Isn't it just the difference between the angles of V and Z?
Yep. Yeah, so basically it's just as simple as saying if I have phi V, well, the way I think of it is the key relationship is Ohm's law. V equals I times Z. So phi V equals phi I plus phi Z. And we know right now phi V in this problem is 0 degrees. Phi I we don't know. And phi Z was, I think we said 5.71 degrees. So what that says is that I has a magnitude 8.375 with an angle of negative 5.71 degrees. Okay. Now, when we talk about a little bit more on Wednesday, is we sometimes refer to this situation where I have a negative, so where my, let me ask this. Let's draw the vector here. So V, if I were to draw the phasor for the voltage was 120 angle 0. So where is that? 120 angle 0, where is that in the complex plane if I draw that phasor?
The second quadrant.
120 angle 0?
It's a
Oh, sorry,
Axis,
it'd be
the real axis.
Yeah, the
Place
real
it.
axis. Yeah, and I think what you were talking about, Parker, is that, yeah, okay, I'd have something here for my current. Here's I, and here's V. But when I have a situation like this, the vector with the more negative angle, I call lagging, okay? So I say, we use that term early on when we introduced impedance, we say I is lagging V. So sometimes what I would say is that this load is a lagging load. All right. And so we're gonna use this term and say this guy has a lagging power factor. So that's the one last piece that we'll introduce on Wednesdays. Sometimes there's a lagging power factor. Sometimes there's a leading power factor. The lagging or leading term, the lagging term means the current is lagging the voltage.
I have a negative association with lagging, probably due to video games. But what does like lagging actually mean?
Lagging means that it's behind. So if I talk to the way I think about this, I don't like the terminology either. It has nothing to do with video games. But right, if this is my voltage, my current would be peaking later.
Is that a good thing or a bad thing? It sounds like a bad thing.
It sounds bad because you think of lagging as bad, right? Lagging just means it's behind. So so if this guy peaks at t equal to 0, this guy peaks a couple seconds later or a couple milliseconds later. If his peak happened earlier, you'd say leading. So it
This is
doesn't,
something to factor in calculation.
I don't like the terms lagging and leading, but they're standard, so I use them.
so it lags or leads by an angle.
It lags or leads by an angle. So we always refer to, when we use the terms lagging or leading, we talk about what's the current doing relative to the voltage. So if the current is behind the voltage, it's lagging. If the current's ahead of the voltage, it's leading.
And when they're the same.
When the same, they're in phase. Yeah, it's unity power factor, we call that. Most of the time when you deal with these problems, they're going to be lagging or leading. You're really never going to have the unity because the problems become too simple then. Yeah.
It's not a weird question. When you say peak, you're talking about it reaches its
Peak means its highest value, yeah. Which by definition is the amplitude of a waveform is its peak value, right? All right, so that's it for today. We will deal with some more examples. I'm going to talk a little bit more about transformers at the beginning of class. We have a transformer problem that's on the homework as well, and we're gonna deal with transformers in the context of power quite a bit. All right. I'm going to